Okay, this video I'm just going to look at another piecewise function. This piecewise function is defined three different pieces or three different equations, and we're going to graph it. So notice I call this function g. Just a little variety. Not every function is going to be named f. Okay, so there's my very squiggly axes. Not very straight, but that's okay. So I'm going to first graph this piece. This is the piece g at x is equal to 5. So the curve I'm graphing here is y equals 5. And this applies when x is less than 0. So to the left of the y-axis. All these values are negative x's. So what does the curve y equals x look like? Well, it's not a curve, really. It's a line. It's a horizontal line at y equals 5. So I'm dealing with just a horizontal line. That should be horizontal. It's so unhorizontal I have to redraw it. There's a slightly better horizontal line. And we're going to have an open circle. Open circle because we're not including 0. So this is one piece. For this piece, we've got an exponential curve. So y is equal to 2 to the x. And this applies between 0 and 1, including 0 but not 1. So you have to remember what an exponential curve looks like. An exponential curve starts, the y-intercept is always 0, and then it goes up and up and up and up, and has a horizontal asymptote approaching 0. So remember, I've graphed it. I said we could do this. We could graph it sort of for the whole thing, and then we'll just fill in the parts we want. So we start at 0, x equals 0. We were at 1, and we'll fill that in with a solid circle because we're including 0. And then this doesn't apply. This function only applies from 0 to 1, so not for very long. So just up to this border point at x equals 1, and then we're going to put an open circle, and the height of that point, well, it should be 2, because if we put 1 into this, we'd be at 2, so we have an open circle at 2. And then I'll just erase the rest. I don't want this. I just put it in because just to help me see what the exponential curve would look like. So now I'll go back, grab my pen. And now I'm going to graph this part, and that's an easy one. That's just a linear equation. Y equals x plus 1. Again, a little tricky to draw because you're dealing with, you want to start on your y-intercept, but the y-intercept is not part of the domain I want. I only want to do x bigger than 1. But again, I'll just I'll draw the whole line. So the whole line looks like that, and then I'll just make it dark for the part that I actually want. And I'll erase the part I don't want. Didn't want that part. I don't want this part down here. And I need to fill in. A solid circle here. So even though it was for the exponential part, it was open, but for this part, I fill it in solid because it's an equal to. So these two pieces actually meet at this value x. When x equals 1, they both have a height of, or a y value of 2, right? If you subbed in 1 to this one and this one, you get y equals 2. So these two pieces actually meet, so it's continuous at this point. So you end up with a solid circle. It was open from here, but then you fill it in from here. But the function itself is not continuous because at x equals 0, there is a jump discontinuity. But good example, because we do see that it's possible that even though it's piecewise here, you still get a continuous function, at least at this value. Okay, and also I just wanted to see an example where there was sort of 3 different pieces. That can happen. You could have as many pieces as you want. You don't usually get too many more than 3, but It happens. Let me do another one. Here's an interesting way to define a piecewise function. So let's graph, I'm going to call this one h. So I'm going to define it as the number -1 if x does not equal 1, and as, what other types of, let's just, I'm not creative, x squared plus 1 if x equals, let's do this, this is not equal to, and then this will be if x equals 1. That's better. Okay. So we'll draw our axes. So notice this function is, like, think about this domain, x not equal 1. So for all values where x is not 1, so the only issue here is at the point, at the sort of line, or when x is equal to 1. When x is equal to 1, we're defined this way, and everything else, as long as x does not equal 1, we have a parabola shifted up 1. So it's almost always defined as this parabola. Right? So I'm just going to draw the parabola for the whole thing. So there's my parabola x squared plus 1. So the function is almost always like this, except at this number here, whereas x equals 1. So at that point, I'm going to have to erase this and put an open hole. So the function is defined as this parabola everywhere except at this one spot where we have an open hole. When x is equal to 1, our function is defined as -1, so the y value is going to be -1. So we're going to have a solid circle way down here at -1. So the function, I mean, it's kind of an unusual looking function. It's going along, nice parabola, 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 and then we sort of jump down to this one point, and then jump back up, and then go along parabola, parabola, parabola. So this, again, you could say this is not continuous. And we call this one a removable discontinuity because it's sort of like you just picked a point out and removed this one single point and put it somewhere else. Sometimes we just say it's a point discontinuity. A point discontinuity often means there's just the hole, and then the function doesn't even exist down here. But this one, it does exist down here, so we'll call this one a removable discontinuity.